This is Dreamtime Science, where we turn fascinating discoveries into bedtime companions. Tonight's journey promises something genuinely intriguing. You know what's fascinating? I've been thinking about how something as simple as electricity can suddenly flow without any resistance at all, like a magical highway with no speed limits or traffic jams. There's something remarkable about superconductors, these special materials that could quietly change the way we power our world and even how we travel, and I can't wait to share what makes them so extraordinary. Should these dreamy explorations accompany your journey to sleep, a gentle like or subscription would be deeply appreciated. What questions about our universe keep you wonderfully curious? First, let's create the perfect space for learning. Cocoon yourself in comfort, release any lingering tension, and let your breath become soft and steady. In the hush of night, as the world outside your window softens into shadow and the air vibrates with the silent hum of distant transformers, let us slip quietly into a realm where electricity and magnetism entwine in an endless, intricate dance. Here, in this twilight between dreams and waking, we begin our journey with a question as old as the first spark that leapt from amber to fur. What truly happens when a material surrenders utterly to the flow of electric current? What secret doors open when resistance, that ever-present adversary, is banished, not merely lessened, but erased completely? Let us linger for a moment in the electric dreams of the past. Imagine the wonder of the 19th century physicist peering into the heart of matter and finding a world alive with motion and force. In those early days, electricity was a wild and mysterious spirit, a force that leapt from chemical cells, raced through copper wires, and set iron filings quivering in neat, invisible patterns. The laws that governed it, Ohm's law, Faraday's induction, Maxwell's grand equations, were still being etched into the stone of human knowledge. Yet, for all this progress, one stubborn fact loomed large. No matter how perfect the wire, how pure the metal, how careful the craftsman, electric current always encountered resistance. Push a current through a wire and the wire grows warm. Power lines hum with wasted energy, the friction of countless electrons jostling through a maze of atomic obstacles. Resistance, it seemed, was as fundamental as gravity or the passage of time. But nature, as it so often does, harbored a secret beneath the surface, a truth so strange that it would take decades to fully grasp. The story begins in 1911 in the chill of a Dutch laboratory where Heike Kamerlingh-Onnes and his team worked in the frigid embrace of liquid helium. Their aim was simple: to measure the resistance of mercury as it was cooled further and further toward absolute zero. At first, the resistance dropped slowly, as expected, but then, suddenly, as though a switch had been thrown, it vanished. Not shrank or diminished, but collapsed utterly, as if the wire had become an unbroken highway for electrons, a path untroubled by even the tiniest bump. The phenomenon was christened superconductivity, and with it a new chapter in the story of electricity began. In this world, wires could carry current forever without losing energy, loops of current could flow for centuries without fading, and magnetic fields could be locked and frozen as if by magic. It was as if the material itself had slipped into a new state, a kind of quantum dreamtime where the old rules no longer applied. But what truly is a superconductor? To answer this, we must first visit the world of atoms and electrons, where the dance of particles forms the foundation of our reality. In a normal conductor, say a copper wire, electrons are free to move, but their journey is fraught with obstacles. The metal is a lattice of positively charged atoms, vibrating and jostling in their thermal motion. As electrons drift through, they scatter off these atoms, losing energy as heat. This endless game of pinball is the source of electrical resistance. Now imagine lowering the temperature. The atomic vibrations slow, the obstacles shrink, and resistance falls, but only so far. Even at the coldest temperatures, some resistance remains, unless you cross the threshold, the critical temperature, where something extraordinary happens. In a superconductor, the electrons pair up, forming what are called Cooper pairs, named for the physicist Leon Cooper. These pairs move in a coordinated wave-like motion through the crystal lattice, gliding effortlessly, immune to the usual scattering that plagues solitary electrons. The material shifts into a collective quantum state, a single, unified entity, like a flock of starlings wheeling as one through the dusk sky. This pairing is fragile. Heat, impurities, or strong magnetic fields can break it, returning the material to its mundane, resistive state. But within the bounds of their domain, superconductors are peerless, perfect conduits, immune to loss. There is, however, another marvel to contemplate. If you were to bring a magnet near a superconductor, you would observe a phenomenon both beautiful and strange. The magnetic field is expelled, pushed away from the heart of the material, as if the superconductor were cloaked in an invisible shield. This is known as the Meissner effect, and it is as fundamental to superconductivity as the absence of resistance itself. It is this property that allows superconductors to levitate magnets, an effect that has become the iconic image of the field, inspiring generations of dreamers and storytellers. The world took notice. In the decades that followed, armies of scientists sought to unlock the secrets of superconductivity. At first, it was a cold and unforgiving domain, accessible only at temperatures near absolute zero, a realm reserved for the most determined researchers, armed with cryogenic baths and patience. Materials like lead and niobium became the workhorses of early superconducting research, their critical temperatures mere handfuls of degrees above the lowest possible point on the thermometer. Still, the promise was too alluring to ignore. Science fiction writers seized upon the idea, weaving tales of levitating trains, perfect energy grids, and computers that could operate with unspeakable speed. In the popular imagination, superconductors became a symbol of the future, a technology both tantalizing and distant, forever just out of reach. And yet, beneath the surface, quiet revolutions brewed. The theory of superconductivity, birthed in the 1950s by Bardeen, Cooper, and Schrieffer, and forever known as BCS theory, revealed the quantum roots of this phenomenon. The electrons, so often thought of as solitary travelers, were in fact participants in a vast, interconnected web, their fates entwined by the vibrations of the lattice itself. The very fabric of matter, when coaxed into the right conditions, could give rise to behaviors that defied classical intuition. It is worth pausing here to reflect on the strangeness of this quantum world. In our everyday experience, materials behave according to rules we can see and touch. Glass shatters, wood burns, metals conduct. But at the quantum level, new possibilities emerge. Particles can become waves, states can blur and overlap, and entire systems can act in concert as a single quantum object. Superconductivity is one of the purest expressions of this hidden order, a reminder that the universe is not merely stranger than we imagine, but stranger than we can imagine. As the 20th century drew on, the dream of practical superconductors began to shimmer tantalizingly closer. In the 1980s, researchers discovered a new class of materials, ceramic compounds containing copper and oxygen, known as cuprates, that became superconducting at much higher temperatures. No longer confined to the frigid embrace of liquid helium, these materials could operate in the relatively balmy bath of liquid nitrogen, a far more accessible and affordable coolant. The discovery sparked a global frenzy as laboratories raced to push the critical temperature higher, chasing the elusive goal of room temperature superconductivity. The visionaries who imagined cities aglow with lossless power, trains floating on cushions of magnetic force, and computers blazing with quantum speed found new hope. The world of science fiction edged closer to reality, and the line between the possible and the fantastical began to blur. Yet, for all these advances, superconductors remain enigmatic. They are at once a triumph of human ingenuity and a stubborn reminder of nature's complexity. Some materials, like elemental mercury, enter the superconducting state with elegant simplicity. Others, like the cuprates, are tangled knots of chemistry and quantum mechanics, their secrets still only half understood. New classes of superconductors, iron-based, organic, even those containing hydrogen squeezed under titanic pressures, continue to surprise and confound. Outside the laboratory, the applications of superconductors are both subtle and profound. In the hidden hearts of particle accelerators, superconducting magnets steer beams of protons at nearly the speed of light, probing the fabric of existence. In hospitals, magnetic resonance imaging machines peer deep into the human body, their images made possible by superconducting coils. Power cables, still rare but growing in number, carry currents across cities with almost no loss, silent and invisible arteries of energy. And always there remains the dream, the vision of a world transformed, where the laws of resistance and waste are set aside and energy flows as freely as thought. The idea of superconductors has become more than a technical achievement. It is a symbol, a cipher for all the futures that might be. In the hands of storytellers, it is the stuff of floating cars and impossible machines. In the minds of scientists, it is a frontier as vast as the quantum sea. Consider, if you will, the magnetic field, a force both familiar and mysterious. For centuries, humans have known its touch, from the gentle swing of a compass needle to the invisible bonds that tether us to the planet's core. Magnetism is the sibling of electricity, bound together by the equations of Maxwell, inseparable as night and day. Yet in the presence of a superconductor, magnetism is rebuffed, reshaped, even trapped. The interplay between the two, electric dreams and magnetic fields, forms the heart of this strange new world. It is no wonder, then, that superconductors have captured the imagination of so many. They are the material embodiment of a paradox, perfect order born from chaos, infinite flow from the stillness of near absolute zero. They invite us to question our assumptions, to imagine what might be possible if we could truly master the forces that run beneath the skin of reality. In the soft darkness of your room, as the night deepens and the house settles into silence, you might find yourself pondering these mysteries. What would it mean to hold a piece of the future in your hand, to command currents and fields with a mere gesture, to walk in a world where resistance has been tamed? The promise of superconductors is not just in the technologies they might enable, but in the doorways they open, doorways into the deeper workings of nature and into the limitless landscape of our own curiosity. As we drift onward, the boundary between science and story blurs. The superconductor is at once a substance, a theory, a dream, a meeting place where the laws of the universe bend and new possibilities unfold. In the next turning of our journey, we will follow these electric dreams into the frontier of discovery, tracing the path from quantum pairing to the mighty magnets that shape our modern world. But even as we chase these visions, let us pause in this moment, suspended between what is known and what is possible, the gentle hum of potential filling the night. In the deep silence of a laboratory, where chilled copper pipes snake along the walls and the air hums with the quiet potential of discovery, there exists a kind of music that no ear can hear, a song made not of sound but of motion, of electrons gliding in unison through a lattice of atoms. This ballet, delicate and profound, is the hidden pulse of superconductivity. To begin to understand this dance, we must shrink ourselves down, far smaller than a grain of dust, smaller even than the cells of your body, until we are adrift among the atoms themselves. Here, in the crystalline framework of a metal, The world is a landscape of repeating order, atoms arranged as if by an unseen jeweler, each nucleus orbited by a cloud of electrons. At ordinary temperatures, this realm is alive with chaos. Atoms vibrate, jostling for space, while electrons dart and careen, colliding with atoms and with each other, scattering energy in the form of heat. This is the ordinary state of metal, the resistance to electrical flow, the reason wires warm when current passes through them, the reason a copper coil heats in your toaster, the reason our machines lose energy even as they work. But as we descend into the chill, as the temperature drops far, far below freezing, something extraordinary begins to happen within certain materials. At first, the atoms shiver and slow, their vibrations muted by the cold. The electrons, feeling the quiet settle in, find themselves less harried by the thermal commotion of the lattice. Yet this alone does not birth superconductivity. For that, we must look deeper, to the subtle and almost paradoxical relationship that forms between the electrons themselves. Electrons, by their very nature, are contrary creatures. Each carries a negative charge, and as every schoolchild learns, like charges repel. You might expect, then, that electrons would keep a respectful distance from one another, forever at odds, never forming pairs. Yet in the world of superconductors, something astonishing occurs. Electrons do pair up, not in the fashion of dancers holding hands, but in a way dictated by the quantum rules that underlie all matter. These pairs are known as Cooper pairs, named after the physicist Leon Cooper, who first described their formation. The dance begins when an electron, gliding through the lattice, attracts the positively charged atomic nuclei ever so slightly, causing a tiny, almost imperceptible distortion in the fabric of the crystal. This distortion lingers for a brief moment, and as the first electron races ahead, another electron, far away in energy terms, but close enough in space, feels the tug of this distortion. Against all expectation, this indirect interaction can overcome the natural repulsion between electrons. The result is a gentle binding, a quantum pairing, as if two dancers, separated by a crowd, are drawn together by the subtle sway of the floor beneath their feet. These Cooper pairs move through the lattice not as individuals, but as a single coordinated entity, their motions synchronized in a quantum waltz. Every pair is aware of every other, their identities blurred by the rules of quantum mechanics, so that disturbing one is to disturb them all. This collective state is called a condensate, and it is this that gives superconductors their most remarkable property, the ability to carry electrical current without resistance. To appreciate how strange this is, consider the usual fate of electricity in a wire. There, electrons bounce from atom to atom, losing energy with each collision, the way a ball loses speed as it ricochets around a pinball machine. This scattering is what causes resistance, and resistance is why power lines hum and machines warm to the touch. But in a superconductor, the Cooper pairs slip through the lattice as if it were utterly smooth, encountering no obstacles, suffering no loss. The current flows forever, unimpeded, looping around a ring for years without any external push. It is as if friction itself has been banished from this microscopic world. The birth of superconductivity, first observed by Heike Kamerlingh Onnes in 1911 with mercury cooled to the bitter cold of liquid helium, was a shock to physicists. For years it remained a mystery, an inexplicable quirk of low temperatures. Only in the late 1950s did the trio of Bardeen, Cooper, and Schrieffer, whose names now grace the BCS theory, provide a mathematical framework for this quantum choreography. Their equations described how, below a critical temperature, the entire population of electrons could collapse into this paired coherent state. The energy required to break a Cooper pair became a kind of barrier, protecting the superconducting order against the disorder of the world. Yet, for all its elegance, the BCS theory is not the whole tale. Its predictions work beautifully for so-called conventional superconductors, simple metals and alloys, cooled to within a breath of absolute zero. But in the 1980s, the discovery of high-temperature superconductors, materials that shed their resistance at temperatures far higher than liquid helium, upended the field. These copper oxide ceramics, complex and brittle, seem to break all the rules. Their electrons paired up not through the gentle mediation of lattice vibrations, but through a mechanism still shrouded in mystery. Some physicists speak of magnetic fluctuations, of hidden patterns in the spins of electrons, of exotic quantum entanglements. The dance of electrons in these materials is more frenetic, less polite, perhaps a tango rather than a waltz, and no one yet knows the full choreography. If you could peek into the heart of a superconductor, you would find not only the absence of resistance, but also another marvel, the expulsion of magnetic fields. This is the Meissner effect, the defining signature of a true superconductor. Place a magnet near a cooled superconductor, and the magnetic field lines are bent and cast away, as if the material had become perfectly diamagnetic. This is why a magnet can levitate above a superconducting disk, held aloft by invisible hands, spinning serenely above the cold, silvery surface. The explanation, again, lies with the Cooper pairs. Their coordinated motion creates currents on the surface of the superconductor, generating magnetic fields that exactly cancel those trying to penetrate from the outside. The result is a fortress, a zone where no external magnetic field can enter. This interaction between superconductivity and magnetism is delicate. Strong enough magnetic fields can disrupt the fragile pairing of electrons, shattering the condensate and restoring ordinary resistance. Each superconductor has its own threshold, its own critical field beyond which the magic collapses. It is here that the limits of our understanding are most sharply drawn, for the interplay of temperature, magnetic field, and the microscopic structure of the material creates a landscape rich with unanswered questions. For practical purposes, superconductors are both a promise and a puzzle. The wires that might one day carry power without loss, the magnets that shape the beams in particle accelerators, the sensors sensitive enough to detect the faintest magnetic whispers of the human brain. All these rely on our ability to control and understand the quantum ballet within these materials. Yet, to date, most superconductors require cooling to temperatures far below what is convenient or economical. The search for a material that will superconduct at room temperature or even at the chilly night air is a quest that drives laboratories around the world. Each new discovery is greeted with excitement, each candidate scrutinized for the telltale signs, the sudden drop to zero resistance, the expulsion of magnetic fields. But what of the electron pairs themselves? Their existence is not just a theoretical abstraction. In certain experiments, the energy gap that protects the superconducting state can be probed directly, measured by tunneling electrons across a thin barrier. The results confirm that, in the superconducting phase, the electrons are indeed bound into pairs, behaving as a single quantum entity. Break a Cooper pair, and you must pay an energy price, a toll that marks the border between the superconducting and normal states. This energy gap is a kind of fingerprint, unique to each material, a clue to its inner workings. The quantum nature of the superconducting state leads to phenomena stranger still. In a narrow ring of superconducting material, the current must wind around in whole number multiples of a basic quantum of magnetic flux. This quantization reveals itself in delicate interference experiments, where the phase of the superconducting wave function, the collective identity of the Cooper pairs, can be twisted and measured. Devices called SQUIDs, superconducting quantum interference devices, exploit this sensitivity to measure magnetic fields with exquisite precision, capable of detecting the faint flutter of a neuron firing or the whisper of the Earth's geomagnetic field. The dance of electrons in a superconductor is not always peaceful. In some materials, the Cooper pairs jostle for space with magnetic order, competing for the favor of the underlying lattice. In others, disorder and impurities disrupt the choreography, scattering pairs and breaking the symmetry. The boundary between the superconducting and normal states can be sharp or blurred, depending on the purity of the crystal, the alignment of the atoms, the presence of defects. At the edge of the superconducting phase, strange and beautiful phenomena emerge. Vortices of magnetic flux, swirling like miniature whirlpools, threading their way through the material, each carrying a precise quantum of magnetic field. These vortices can move, pin, and interact, giving rise to complex behaviors that challenge our understanding. The search for new superconductors is a voyage into the unknown. Chemists combine elements in novel ways, layering atoms in intricate architectures, probing the limits of stability and order. Physicists model the interactions between electrons, weaving together mathematics and intuition, peering into the quantum shadows. Each new material is a fresh canvas for the dance of electrons, a chance for nature to surprise us once more. Yet even as our knowledge grows, the fundamental mystery remains. Why do some materials, and not others, allow their electrons to waltz together in perfect harmony? What hidden rules dictate the formation of Cooper pairs, the expulsion of magnetic fields, the fragile coexistence of superconductivity and magnetism? The answers are elusive, scattered across the landscape of quantum mechanics, condensed matter physics, and materials science. The boundaries are not sharp, the puzzles are not yet solved. And so we are left with the image of a ballet in the darkness, electrons spinning and swirling through a landscape shaped by cold and order, their motions governed by the subtle mathematics of quantum fields. The superconductor is both a triumph and a mystery, its properties exploited in the laboratory, its secrets still half hidden. Outside, above the silent laboratory, the night deepens and the world seems still. But in the realm of the very small, the dance of electrons continues, unbroken, unyielding, a hint of something greater lying just beyond the edge of understanding. It is here, at this shimmering boundary between the known and the unknown, that we must linger a while longer, peering into the darkness, waiting for the next step of the dance to reveal itself. A hush falls over the laboratory as the clock edges toward midnight, the hour when the world's distractions fade and only the hum of earnest inquiry remains. Here, among the silent instruments and softly blinking lights, the air feels heavy with anticipation. It is in such sanctuaries of curiosity that the invisible qualities of matter are summoned into the visible world, where the stubborn secrets of nature are teased out, layer by layer, by hands both patient and clever. In this realm, the study of superconductivity has unfolded not as a single flash of revelation, but as a gradual unveiling, a dance between observation, inspiration, and methodical craft. To understand what it means to pursue superconductivity, one must first appreciate the difficulty of seeing what does not wish to be seen. Superconductors are, by their nature, elusive. Their most extraordinary qualities, perfect conductivity, the expulsion of magnetic fields, are not revealed under the warm gaze of everyday experience. Instead, they emerge only under circumstances that seem almost otherworldly. Temperatures so low that atoms themselves barely tremble, magnetic fields sculpted with exquisite precision, and measurements sensitive enough to detect the faintest whisper of resistance or the total absence thereof. The story begins, as all great stories do, with a question. At the dawn of the 20th century, physicists wondered how the electrical resistance of metals would behave as they were cooled to ever lower temperatures. Would the resistance fall smoothly to zero, or would some unknown law intervene? The journey toward an answer took researchers into the very heart of cold. One of the earliest pioneers was Heike Kamerlingh Onnes, a Dutch physicist who was both an artisan and a dreamer. In his laboratory at Leiden University, Onnes became the first person to liquefy helium, achieving temperatures just a few degrees above absolute zero, a frigid domain, colder than any natural place on Earth. With the chill of liquid helium at his command, Onnes could at last test the metal's resistance far below the limits known to his contemporaries. On a day in April 1911, Onnes and his team cooled a slender wire of mercury, lowering its temperature step by cautious step. They watched as the resistance dropped, just as theory hinted, until quite suddenly it vanished altogether. Not decreased, not merely diminished, vanished. The wire became a perfect conductor, immune to the usual friction of electrical flow. Onnes had discovered superconductivity, though he could not yet know the full profundity of what he had witnessed. The experiment was simple in its principle, but profound in its execution. A current was sent through the mercury wire, its resistance measured with extraordinary care. The readings told a silent story. At 4.2 Kelvin, the mercury's resistance was simply gone, as if the wire had become a highway without a single bump or barrier. In that laboratory, in the hush of the ultra-cold, a new chapter of physics was born. Yet the invisible properties of the superconductor were not content to rest in silence. Soon, questions arose. What was happening inside the metal? How could resistance, so stubborn in every other context, simply disappear? It would take decades and the efforts of generations to unravel these mysteries. The pursuit of understanding required new tools and new ideas. Scientists began to probe superconductors with magnetic fields, suspecting that the interplay of electricity and magnetism might reveal the hidden mechanisms at work. One of the earliest and most dramatic discoveries was made by Walter Meissner and Robert Oxenfeld in 1933. They cooled a piece of tin in the presence of a magnetic field and observed a startling phenomenon. Below its critical temperature, the tin expelled the magnetic field from its interior entirely. The effect was so complete that the field lines curled around the superconductor, leaving its core untouched. This was not merely a passive consequence of zero resistance, it was an active expulsion, a new state of matter, later named the Meissner effect. To detect this, Meissner and Oxenfeld used delicate coils wound around their sample, measuring the minute changes in magnetic flux as the metal underwent its transition. The experiment required patience, precision, and a certain stubborn faith that nature would reveal something intelligible if only they listened closely enough. Their discovery showed that superconductivity was not just about perfect conduction. It was also about a profound transformation in the way matter interacted with the magnetic world. This expulsion of magnetic fields led to a host of ingenious demonstrations. One is the phenomenon of magnetic levitation. A small magnet, placed above a cooled superconductor, will float serenely in mid-air, held aloft by the invisible repulsion of the Meissner effect. The image is almost magical. A dance of forces seen and unseen, a glimpse into the hidden symmetries of the universe. But beneath the spectacle lies careful experiment, mathematical insight, and a relentless drive to understand. As the decades unfolded, scientists devised ever more subtle ways to peer into the heart of superconductivity. They measured the critical temperature, the precise point at which resistance disappeared, for every material they could chill. They mapped the critical magnetic fields, the strength of magnetism that a superconductor could endure before its special state was broken. Each experiment added a brushstroke to a growing portrait, but the face of the mystery still refused to resolve. Theorists, too, joined the hunt, seeking patterns and explanations that could unite the avalanche of experimental facts. It was not until 1957, nearly half a century after Onnes' initial discovery, that three physicists, John Bardeen, Leon Cooper, and Robert Schrieffer, offered the first convincing theory. Their model, known as BCS theory, proposed that electrons in a superconductor did not move as solitary wanderers, but as pairs, Cooper pairs, bound together by a subtle interaction with the crystal lattice of the metal. To test these ideas, experimentalists devised new measurements of the energy required to break these pairs, to nudge an electron out of its cooperative dance. Techniques like tunneling spectroscopy emerged, where a thin insulating barrier separated a superconductor from a normal metal, allowing electrons to tunnel through the barrier in ways that revealed the underlying energy structure. These experiments required not only technical mastery, but also a willingness to believe in the reality of quantum mechanics, a domain where particles could behave like waves and where the impossible became routine. The pursuit of higher and higher critical temperatures became a kind of scientific grail. For decades, the known superconductors were all metals or simple alloys, and their critical temperatures never rose far above the temperature of liquid helium. The chilling necessity of helium, rare and costly, kept superconductivity an exotic curiosity confined to a handful of specialized laboratories. Then, in 1986, a seismic shift occurred. Two researchers working in Zurich, Georg Bednorz and K. Alex Müller, discovered that a class of copper oxide ceramics, materials previously thought to be unremarkable, could become superconducting at much higher temperatures. Their breakthrough came not from the march of theory, but from a willingness to experiment with the unlikely, to listen to the odd whispers of chemistry. The critical temperature they found, around 35 Kelvin, was astonishing. Soon, other groups pushed this limit even higher. Within a year, superconductivity in certain materials was observed above the boiling point of liquid nitrogen, a far more accessible coolant than helium. The world of experimental superconductivity was transformed overnight. Laboratories everywhere raced to synthesize new compounds, to measure their properties with ever greater precision, to understand the delicate interplay of atoms that allowed such extraordinary behavior. The techniques became ever more elaborate: X-ray diffraction to determine atomic structure, neutron scattering to probe magnetic interactions, angle-resolved photoemission spectroscopy to map the energy landscape of electrons. Each method peeled back another layer of invisibility, revealing more of the strange kingdom that superconductors inhabit. Yet the experiments remained, at their heart, exercises in careful listening. The resistance measurements, so fundamental to Onnes's original discovery, were now performed with electronics capable of detecting changes of 1 part in a billion. Magnetic susceptibility, the way a material responds to a magnetic field, was measured with devices sensitive enough to feel the tug of a single quantum of flux. Scientists cooled their samples in elaborate cryostats, bathed them in fields that could be tuned with exquisite accuracy, and watched as the boundaries of superconductivity shifted and danced. One of the most hauntingly beautiful experiments in the study of superconductors is the observation of quantum vortices, tiny whirlpools of magnetic field that can thread their way through certain types of superconductors. When a magnetic field is strong enough, but not sufficient to destroy superconductivity completely, it can penetrate the material in discrete, quantized bundles. Each vortex is a silent witness to the quantum nature of the superconductor, a place where the order is twisted but not broken. With the aid of magnetic force microscopes, scientists have learned to visualize these vortices, watching as they arrange themselves in intricate lattices, move in response to currents, or become pinned by defects in the material. Such experiments require an almost monastic dedication to detail. The preparation of flawless crystals, the alignment of fields and currents with microscopic accuracy, the maintenance of cold so deep that even the faintest warmth would spoil the effect. Yet the reward is a direct glimpse into the quantum realm, a chance to see, if only fleetingly, the strange choreography, that underlies all superconducting matter. The pursuit of superconductivity has also driven the invention of entirely new measurement techniques. The SQUID, or superconducting quantum interference device, is a marvel of experimental ingenuity. It exploits the quantum phase coherence of superconductors to detect unimaginably small magnetic fields, even those produced by the firing of a single neuron in the human brain. By threading a loop of superconducting material with carefully controlled magnetic flux, the SQUID can reveal the presence of a field as tiny as a few femtoteslas, a millionth of a billionth of the Earth's own magnetic field. These devices have become the eyes and ears of low-temperature physics, capable of perceiving the invisible with clarity that borders on the miraculous. Through all these experiments, a pattern emerges, not just in the data, but in the method of discovery itself. The pursuit of superconductivity is a testament to the power of persistence, of creative adaptation, of the willingness to try the untried and to measure the immeasurable. It is a story woven from countless hours, from the careful tuning of apparatus, from the patient recording of results that at first seem mundane, but which, in the fullness of time, reveal new laws of nature. And always the invisible beckons. There are superconductors that behave in ways no theory has yet explained, materials whose critical temperatures defy expectation, phenomena at the boundary between order and chaos. As new compounds are synthesized, as measurement techniques grow ever more sensitive, as computers model ever more complex interactions, the frontier of understanding continues to recede, beckoning the curious onward. It is late now in the laboratory, and the air is heavy with the quiet satisfaction of discovery, mingled with the ever-present sense of how much remains hidden. The instruments are still, the samples cold and silent, the data waiting to be deciphered. Yet even as this night of inquiry draws on, one can sense the promise of what lies ahead, the next question, the next experiment, the next glimpse into the world behind the curtain. In the darkness, a faint blue glow flickers from a monitor, tracing the signature of a superconducting transition, a sudden drop to zero, a sign that the invisible has become, if only for a moment, visible. And somewhere, just beyond the reach of comprehension, the riddle of superconductivity lingers, unresolved, inviting us onward, deeper into its quiet, endless night. In the quiet hours, when the world slips into stillness, the mind is free to wander across the landscapes of possibility. It is here, in this hush of expectation, that we may turn our gaze forward and contemplate the gifts and enigmas that superconductors promise to bestow. If the story of their discovery is a tale of patient curiosity, and their applications a testament to human ingenuity, then their future is a horizon painted with questions as well as hope, an unfinished canvas where physics, technology, and philosophy intermingle in the half-light of what may yet be. Imagine a city at dawn, the air alive with the hum of unseen energy. Beneath the streets, not copper, but slender threads of superconducting material snake through the earth, conveying electrical power with absolute fidelity. No warmth radiates from these cables, for no energy is lost in their passage. The city's heart beats with the pulse of an unblemished current, its lifeblood coursing without resistance. The era of wastage, of losses to heat and inefficiency, has receded into history. Every joule summoned at the generator's birth arrives, undiminished, at its destination. Such a vision is not sheer fantasy, but a glimmer of what might unfold. Today, the wiring of civilization is a patchwork of compromise, a network where over 5% of all electricity generated is lost to resistance in the wires alone. In the world of superconductivity, this inefficiency could become a relic, a memory of a less precise age. If we could master materials that superconduct at or near room temperature, robust to the rigors of daily life, the transformation would be profound. Power grids could stretch over continents with barely a drop of loss, making renewable energy, wind from the wild Atlantic, sunlight from searing deserts, universally available. The great rivers of energy, now confined by the boundaries of distance and geography, would flow freely and endlessly. But the promise does not rest with electricity alone. In laboratories and research halls, the magnetic fields of superconductors already perform feats of exquisite sensitivity and power. The magnetic resonance imaging scanners that peer gently into the human body, mapping tissues with the clarity of a painter's eye, rely on the steadfast embrace of superconducting magnets. In the future, these instruments may become smaller, cheaper, and more widespread, making the marvel of non-invasive diagnosis accessible to all. Superconducting magnets may also serve as the heart of new particle accelerators, or as the guiding hand in magnetic levitation trains, vehicles that float, silent and frictionless, above their tracks, travelling at astonishing speeds with barely a whisper of energy expended. Yet for all their promise, superconductors remain enigmatic. Their behaviour, so simple in its outward effect, resistance vanishing as if by magic, hides a world of complexity beneath. Though the BCS theory elegantly describes conventional low-temperature superconductors, it falters before the high-temperature variants discovered in the late 20th century. In these materials, cuprates, iron-based compounds and others, the mechanism of superconductivity is still shrouded in mystery. Electrons pair up, yes, but the glue that binds them, the dance that lets them slip through the lattice unimpeded, is not so easily explained. The physics at play may involve spin fluctuations, charge density waves, or subtler, more elusive forces. It is as if the universe has written a riddle in the very fabric of matter, challenging us to decipher it. This mystery is more than academic. The search for understanding is a quest with tangible stakes. If the secret of high-temperature superconductivity is unraveled, it may unlock a new generation of materials, substances that superconduct not at the frigid temperatures of liquid nitrogen or helium, but at the warmth of a summer afternoon. Such a breakthrough would unleash a technological renaissance, sweeping away the logistical and economic barriers that now hem in the use of superconductors. The cooling systems, the exotic materials, the elaborate care, all might become unnecessary. Superconductors would become as ordinary as steel woven into the fabric of daily life. The philosophical implications of such a shift are worth dwelling upon, even as the practical ones dazzle and entice. For what does it mean to discover a phenomenon that so flagrantly defies our intuition, and then to harness it for the common good? Superconductors remind us that nature's laws are not always what they seem, that the world, at its deepest level, is stranger and more generous than we might assume. Here, in the silent motion of paired electrons, we glimpse the unity of quantum mechanics, the way in which the many can act as one, the collective behavior of particles giving rise to properties unimaginable from their solitary actions. This unity, this emergence, is echoed in other fields of science, and perhaps even in the broader currents of human society. Just as electrons in a superconductor move in synchrony, so too do individuals sometimes coalesce into communities, organizations, movements, entities whose actions transcend those of their parts. The superconductor becomes a metaphor, a model for the power of cooperation and coherence. It whispers that there may be ways to move through the world with less friction, less waste, if only we can learn the right dance. Yet even as they inspire, superconductors also unsettle. They remind us that the universe harbors secrets still undiscovered, that our models, however robust, are always provisional. Each new class of superconducting material, each unexpected twist in the story, forces us to revise our theories, to accept the limits of our knowledge. This humility is itself a gift, a gentle admonition to remain curious and open-minded. The horizon of science is always receding, always drawing us onward. The pursuit of room temperature superconductivity is, in this sense, a microcosm of the scientific endeavor as a whole. It is a journey marked by false starts, sudden leaps, and long stretches of patient toil. In the past years, there have been tantalizing reports, hydride compounds under immense pressure, for instance, fleetingly superconducting at temperatures that seem almost mundane. Yet these triumphs are often fragile, achieved only within diamond anvils, at pressures greater than those found in the deepest ocean trenches. The challenge is to bring these miracles down to earth, to tame them, to weave them into wires and circuits that can survive the rough and tumble of everyday use. And so researchers labor on, guided by both practical necessity and the lure of the unknown. They synthesize new materials, probe them with X-rays and neutrons, map their electronic landscapes with scanning tunneling microscopes. They devise theories, test them, discard or refine them, always searching for the elusive pattern that will unlock the next chapter. In this, they are fellow travelers with the explorers of old, charting the uncharted, motivated by the same blend of curiosity and hope. The implications of success would ripple far beyond the laboratory. Imagine quantum computers, their fragile qubits preserved by superconducting circuits, solving problems in seconds that would take today's machines millennia. Imagine power grids, immune to brownouts and blackouts, their nerves made of lossless conductors. Imagine a world where transportation is transformed, not just trains, but perhaps even spacecraft, their magnetic fields shaped and steered by superconducting coils. The boundaries of the possible would shift, as they have so many times before, pushed outward by the steady advance of understanding. Yet, in all these dreams, there is also caution. Every new technology brings with it the potential for both benefit and harm. The same powerful magnets that heal can also disrupt. The same seamless flow of power can be misused or overburdened. The philosopher's task is not to stand apart from technology, but to engage with it, to ask not just how, but why, and to what end. In the case of superconductors, the questions are many. If energy becomes almost free to transmit, how will societies adapt? If quantum computers proliferate, what will become of privacy, of security? If new materials render old industries obsolete, how will we manage the transition? These are not questions with easy answers, but they are questions worth asking. They remind us that science is not isolated from the world, but braided into its fabric, its discoveries reverberating through economies, cultures, and lives. The story of superconductors is thus not just a tale of electrons and lattices, but of people and possibilities. And still, the mystery endures. For all our progress, there are whispers of phenomena not yet explained. Some suspect that superconductivity lies at the heart of other cosmic wonders, perhaps even in the hearts of neutron stars, where matter is pressed to unimaginable densities and quantum effects rule supreme. The boundaries between condensed matter physics and the astrophysics of the cosmos grow thin. The same principles that govern a laboratory wire may echo in the song of distant stars. The unity of natural law is both humbling and exhilarating. In rare moments, when the night is especially quiet, one may reflect on the strangeness and beauty of it all. The electron, a particle so small as to be almost beyond comprehension, is capable, when joined with its fellows, of conjuring a world without resistance, a domain where energy flows unimpeded, order arises from chaos, and new forms of matter emerge. This is the poetry of physics, the deep music of the universe made audible to those who listen. And perhaps, in contemplating superconductors, we are reminded not just of what we might achieve, but of what we have yet to understand. The future is not a fixed destination, but a field of possibilities shaped by our questions and our courage. Superconductors are a signpost on that path, their properties both gift and challenge, their mysteries an invitation to wonder. So we linger at this threshold, poised between what is known and what remains to be discovered. The harbingers of future horizons beckon us onward, their silent promise shimmering in the liminal space between science and dream. The search continues, the questions deepen, and somewhere, just beyond the edge of what we can yet see, the next revelation awaits, patient and shining in the unbroken flow. As our journey through the shimmering realm of superconductors drifts to a close, like a comet tail fading into the hush of space, we hold the quiet wonder of a future where power and transport dance in effortless harmony. Rest now in this gentle glow of possibility, and when your dreams are ready to wander again, return for more soft-spun mysteries from the stars.